Welcome everybody in the lecture hall. Welcome everybody on Zoom. So this is the second week of the big data course. So last week we had an appetizer, and this week we are going to start getting into the actual material of big data. I will start actually right away with a question. So it's exactly the same as last time. You can go to this address about the app. Let's switch now the screen. Which is about what I told you about the fundamental data shapes of data. So we saw how important it is to understand whenever you query data, whenever you store data, to understand the shape of the data. So one of these is not a fundamental data shape. Which one is it? So is it cubes, tables, trees, circles, graphs? Cubes, tables, trees, circles, graphs. 4 of them are fundamental data shapes. The 5th one is not. Let's see answers coming in. Welcome to those who are joining us. Still answers coming in. Things that it's now stabilizing slowly. Let's look at your answers. You can still modify, send an answer. There is a majority, an overwhelming majority. For circles, is the majority correct? Yes, the majority is correct. So indeed, we saw that tables are the most ancient kind of shape. We have them on clay tablets, thousands of years old. We also have trees, we also have graphs, we also have cubes, we also have text / unstructured, whatever is unstructured, audio, video, and so on. All right, so circles, we'll see actually circles or rings today or tomorrow, but it's not actually a data shape. It's a physical detail of an implementation. All right, so now I'm going to switch back to I have to find my windows again. Let me do it that way. New share. And that should be this one. All right. All right, so let's move on. So one of the examples that I gave you last week is astronomy. So we are trying to map the sky, and it's billions and billions of objects that are out there that we are continuing to disorder. There are still a few that are actually quite strange to us, like these very remote regular people that we have no idea what this is. So there are surveys going on to try to catalog everything we can see. And one such survey cannot understand anything. Is there a problem with the sound? Or the link is that it might be that the connection is not to the room. No, it does say, oh, yes. So maybe when I did the test, I was actually on the laptop. Maybe that was the reason why you could hear me. So how is it looking now? Can you now hear me fine? Yes? All right, because I switched to the Hörsal microphone. All right, so let me continue. Actually, what I was saying is that we're cataloging the sky with everything we can see, and this is a lot of data. These are billions of objects. And if you look at the actual data that was released on the website of the SDSS, it's actually online, you can find it. You will see that there are 273 terabytes of data. If you look at the files and the directories, you will see that we have 680,000 directories and 176 million files. That is enormous. As you can imagine, that is not going to fit on your laptop. And that's exactly why we have to come up with other solutions in order to handle this kind of data, which is exactly the goal of the course and especially of today's lecture. So the question is, how do we deal with 273 terabytes of data spread over 680,000 directories with 176 million files? So we saw that we have good old relational databases, right? So these are the good old 1970s. This is what you studied for most of you during your bachelor's with data models and databases, right? So these are the relational tables. But the thing is, relational databases, at least the classical ones, they are designed to run on a single machine. So you already have your answer. You are not going to fit 200 terabytes in there. That just doesn't work. You need other solutions. Petabytes do not fit on a single machine. Not yet. You know, we don't know the future, but at least it doesn't fit today on a single machine. But the good news is, even though we are going to move slowly to the cloud, we can reuse 99% of what was done in the past, because all the principles that have been invented in the 1970s, like data independence and so on, the relational algebra, the idea of models, query language, and so on, this can all be reused. And this is actually a pretty good news, because we are going to be reusing a lot of things. In particular, we will see in this course projections, selections, grouping, aggregation, sorting, joining, and so on. We will see this. This will not be new to most of you, but this will stay. We will see SQL. We actually have an exercise dedicated to SQL. If you didn't learn SQL before, then here's the moment to actually learn SQL. Make sure you solve this week's exercise. We'll see other declarative languages and functional languages, just like SQL, even though you could argue that SQL is not perfectly functional, but then we'll talk about these things. We'll see optimizations, query plans, indices, and so on. This all stays, right? Everything you've learned. Tables, rows, columns, primary keys, what we saw last week. This is also going to come back in this lecture. We'll have actual tables. But there are a few things that might change, and I already said a few words about that last week. Is that this tabular integrity, domain integrity, atomic integrity, we are going to throw that away. You know, the constraint that you cannot have nestedness, that you cannot have types that do not correspond to their columns, that you cannot have extra values here and there. The normal forms that you have been so cautiously learning during your bachelor's, we are going to throw that all away in that lecture. But as I said, you can only throw them away once you understand what they mean. Right, it's very important. We need to understand what we are doing right here. I want to say a few words about that, because that was a question that somebody asked last time. It was a good question. The definition I gave you of a table as a set of maps, or a list of maps, or a bag of maps, depending on the semantics. So the definition as a set of maps might not be the exact definition that you saw during your bachelor studies, or that you will find in database textbooks, because in database textbooks, typically it's presented as a relation over domains, meaning a subset of the Cartesian product of the domains. But the definition I'm giving to you is equivalent in the sense that if you design everything with a relation over domains, you basically get the relational integrity or the tabular integrity, depending how you call it, the fact that all tuples must have the same attributes, you get that for free if you use the relation definition. The domain integrity you also get for free if you use the relation definition. What you don't get for free is the atomic integrity, because even with the relation definition, the domains could still be non-atomic, right? But basically, if you take my definition, set of maps plus relational integrity plus domain integrity, it is the same as, at least in the intent, as the definition as a relation. As I said, the definition as a relation has a few issues, such as the fact that it puts an order on the columns, which actually we do not have in a database and so on. But I think that defining a table as a set of maps with these three constraints, and then dropping these constraints pedagogically is the best entry into big data, right? Because you just drop constraints, and this is how you get large and messy data sets. So we'll have in this lecture heterogeneous data, yes, a lot of mess, nested data, but this is real life, right? Before you run your data into machine learning pipelines, the data is not going to be perfectly structured, and we'll denormalize data. So the data denormalization brings me to a question. I might have mentioned this last week, but I'd still ask you if you still remember. What shape do you get if you take a table and you denormalize tables? Actually, you might get several of them, right? But do you get cubes? Do you get trees? Do you get graphs? Do you get unstructured text? Or does it not make any sense to denormalize a table? I could express it differently, like, do you get a collection of cubes, a collection of trees, a collection of graphs, a collection of unstructured text, or doesn't make sense? Denormalizing a table. When I say denormalizing, I really mean the full denormalization, right? All the way to normal form 0. Still have answers coming in. Hundreds, 107, 113. Let's start looking at your answers. Aha, this is very interesting. Okay. Is the majority correct? The answer is yes, the majority is correct. We will see, not today, we'll see in a few weeks, but I can still tell you, I mean, even in movies, sometimes they show you the future before they actually play the normal events, right? So I'm showing you the future. We will denormalize tables and actually get collections of trees, right? How? We'll see. But this is the thing. So by now, just remember that by heart, and you will see it will make sense when you actually get into this, because it's mostly because of nestedness. When you start nesting data, you start getting tree-like or arborescent structures. All right. Let me get back to the slides. And normally, again, if I prepared correctly, we should be landing exactly where we were. All right. Okay, so as you see, this is the one thing that changes. We are denormalizing things. We are going to denormalize a lot of things in this lecture and drop constraints. There is something else that's going to change. Remember ACID, this good practice in the monolithic databases, atomicity, consistency, isolation, durability. Well, at least in the early days of big data, we had to drop that. So we very often in large-scale systems, we do not guarantee ACID properties. Instead, we rely on something called the CAP theorem, which I will talk about today. So you'll hear the notion of atomic consistency, which is a bit different from the consistency in ACIDs, availability, partition tolerance, and eventual consistency. These are the things you're going to hear in this lecture. I'm saying for now, because there are people trying to bring back ACIDs to big data, right? So maybe one day we'll finally also recover ACID properties also in a large-scale system, but it's not easy at all, as I'll try to explain to you. All right, so what will we do in that lecture? We are essentially taking a monolithic relational database system or database management system installed on a server, a single server. We're gonna break it apart, look at the components and rebuild everything, but in the cloud. So we are going to see the stack. It's actually, there's a similar stack inside the monolithic database, it's just that it's all hidden, right? But we are going to rebuild that modern big data stack. So we'll have the storage. That's what we are going to do today. We look into Amazon S3, into Azure Blob Storage. There's plenty of other kinds of storage, HDFS, which we will see next week. We'll look into how to encode things. So your computer scientists, I probably won't spend much time on that. You probably already know the actual encodings. UTF-8, by the way, should be now the standard whenever you actually store text for interoperability. We'll look into syntax. CSV for tables, XML, JSON for trees, RDF XML for graphs, Turtle for graphs, XBRL for cubes. And we'll see that why are we doing XML and JSON? Because XML and JSON are denormalized tables, as we will see. And denormalized also means that we'll see data frames that is actually a collection of valid JSON objects. These are data frames or XML nodes. All right, then we look into data models, which is the abstraction of the set syntaxes. So we look into trees, graphs, cubes, graphs and cubes at the end of the semester, but a lot of tables and trees, the denormalized tables, trees. We'll look into validation. This is how we'll get the data frames, right? With JSON schema, JSON, XML schema, relational schemas, you already know, XBRL taxonomy, maybe a little bit of that. We'll look into the processing of data, roughly in the middle of the semester. We'll be starting with MapReduce, which is the first real parallel processing system whose principles still apply even in more modern systems like Spark. We'll also look into Apache Spark, that is a generalized version of MapReduce, but there's many others, but you'll see if you learn one, you've learned them all. Then we look into how to index data, even though a lot of you already saw that because that also exists in relational databases. I told you we are reusing a lot of things, but we'll see that in document stores, which are essentially data stores for denormalized tables, collections of trees. We'll look into key value stores today or tomorrow, hash indices, B trees, B plus trees. There's also geographical indices, spatial indices, and so on. Then we have full data stores that are actually combine all of that into a nice higher level system that is not kind of a full database yet, because we're missing a query language and maybe ACID and so on. So this is why we say data store and not database management system. We'll look into, so RDBMS is the ones you know, right, from the 70s, relational. MongoDB we'll look into, but Couchbase, Elasticsearch, they work just the same. Hive is just, we'll see using SQL on top of HBase. We have HBase as well, MarkLogic, Cassandra, which is an alternative to HBase. These are the white column stores. So we'll look into a lot of these. We'll look into querying the data. I'm not introducing SQL anymore. You know SQL by now, but there's actually other languages because SQL is for tables. Never forget that. SQL is for tables. If you try to use SQL on other data shapes than tables, this is when things will start to become less convenient, difficult, less productive, slower, and so on, which is the reason why we have query languages for other shapes. For trees, we have JSONic, XQuery, Nickel, MDX is for data cubes, Sparkle is for graphs, and REST APIs are a general way. You probably heard of GraphQL, for example, in that respect. So query languages that are declarative and functional languages that hide all of the complexity. And finally, but this is not part of the course, there's also user interfaces, right? You might have spreadsheets, Tableau, you might have heard of that, ClickView, BI tools, and so on. So this is the final user-facing, at least not the tech-savvy user-facing front end. But today, we'll start with storage, because all of that I showed you, that's the whole semester, right? It's not what we are going to do. We are not going to do everything today. So today, we are going to start here at the bottom of the stack with the storage, and in particular with cloud storage. So we need to find a way to go from a single machine environment, for example, your local file system, or PostgreSQL installed on your laptop, and we need to scale that to a full system. And it turns out I also have a question for you regarding that. I have a lot of questions today. Yes, that's what I want to ask you. We'll also talk today, because we are going to the cloud, right? So we need to look at data centers, where this is where all the action is. So my question is, what is there in a data center? Who has already been in a data center? Some of you who never was in a data center. Okay, most of you. So try to guess, maybe you already know, but try to guess. In fact, a few years ago, we organized a field trip to a data center in Zurich. So we went with many people of the class to the north of Zurich near Gadbrook. And we visited a data center. It took us half an hour to get everybody to get in because of the security, just to give you the impression of the military grade security that there are in data centers. So what is there in a data center? Plenty of small cheap machines, says the majority. Some of you think maybe some really big machine with 1,000 core CPU, petabytes of disk, 1 petabyte of memory could also be. At least many people figure that this is what there is in a data center. And a few of you are already ahead of their time with a full-blown quantum computer. Who knows? It will probably arrive someday, right? So we'll see. Well, we actually don't know if it will arrive because that's a big unknown. It's called decoherence, the problem in quantum computers. So it's a big unknown if we can actually push the number of qubits without actually causing decoherence. But we'll see. But in any case, the majority here is correct. Plenty of small, cheap machines. This is what we have in a data center. Let me switch back. Oh, it's 3. All right. So data needs to be stored somewhere. That's basically the idea that some physicists like to put it that way. Information is physical. If you want to store data, it needs to be bits, zeros and ones on some physical medium, right? So here's an insight on databases. There are 2 main paradigms for storing and querying data. 2. One paradigm is the traditional paradigm that you know from good old relational databases. This is a fully integrated database management system like PostgreSQL or any relational database. You need to import the data before you do anything. It all starts with an import of the data. It's also called ETL, extract, transform, load, ETL, which actually is a verb. You can ETL something. And this is the paradigm, like the classical paradigm for good old databases with data independence. The second paradigm is called data lake paradigm. This paradigm is about throwing the data directly on some file system, could be your local hard drive or could be the cloud, as we will see, or HDFS next week. And then you just query the data from where it is. Right? This is called the data lake. If you heard of Python pandas, this is a bit related to these hype technologies. And right now, the 2 coexist, right? So ideally, what Edgar Code would have said is that the right way to do it is with a fully integrated system, as you see on the left, and have everything managed and import and so on and so on. But it's not easy. And we are not quite there of actually having this full-blown paradigm in the cloud. So this is why today we also play with data lakes. Who heard data lake already, the terminology? Right. So this is basically what it is. You have a huge file system and you throw your data on it, no matter what it looks like. Just a huge, imagine a huge mess, right? So I mean, mess is used in the sense, you will see that there will be a paper that will also share with you on data independence for large messy data set. It's really this idea that the biggest challenge in machine learning is the preparation and the cleaning of the data. This is one of the biggest challenges. You might have heard of data-centric AI, data-centric machine learning. All right, so remember these 2 main paradigms. You can either have an integrated system that handles everything and you ETL data inside, and that can be actually very, very fast when you do it that way, or you use a data lake. Today, we'll start with data lakes, right? So we are going to use S3, Azure Blob Storage, and so on. So we'll see how to throw data on in cloud storage and so on. All right. So if we start at the 70s, let's say, the early databases, and we have a single machine, then typically you're going to have a hard drive. The data of the relational database, so the data, what you see on the left here of PostgreSQL, is stored on a single hard drive like this on your computer, desktop, laptop, and so on. Typically also, you already know that the files are organized in directories on your laptop, and you have a hierarchy like that, right? You're computer scientist, I won't stay much on that, right? You also know from probably systems programming, or when you look at computer architectures, that the way that files are stored on your hard drive, this is block-based. You don't read single bits, you read blocks. What's the typical size of a block? Yes? 4 kilobytes, exactly. That's the order of magnitude. It's always an order of magnitude, right? Because you could say, okay, 2 kilobytes, 8 kilobytes, 16 kilobytes would work just as well, right? As long as it's not a gigabyte or 2 bits, right? But this is exactly the order of magnitude. You basically have blocks of 4 kilobytes and you read 4 kilobytes at a time. The reason for that is latency, right? Because if you keep reading bit by bit, especially with a mechanical drive, you're waiting at every bit for the head to move, right? So it's just going to take forever. So this is why that's an idea of batch processing, actually, this idea of block. You consume the bits in batches, and these batches are called blocks. Now you could try to start sharing the data, right? So you could say, okay, you share it over the network, so you can have it on your local machine. You can maybe share your machine over some network and have other people access it. You might even have a network attached drive that everybody can access, right? That would still kind of work. It wouldn't be trivial, but you could kind of make it work in that way. But if you tried to go to what is called wide area network, it's just too many people. There is no way you can actually manage the storage that way. It might work with a relational database, right? Because the relational database will handle the users and so on and so on. But what I'm referring to here is directly sharing your drive. Directly have people read and write from your drive taken as a data lake, right? We are trying to scale the data lake starting with your single drive. So you see there's already a limitation that there is no way you're going to manage to get a wide area network connect to your local hard drive. It's just too much. There is another issue that we have in terms of scale. Who has already done a backup of their computer? Who never did any backup of their computer? Okay, you should. You really, really should, because don't wait for a crash. The crashes arrive. I'll speak about that when we look at fault tolerance. But basically, if you back up your machine, you probably see the number of files that actually get backed up. And if you look at that number, it's typically going to be within that range. You might be surprised actually to see like maybe tens of thousands, hundreds of thousands of files, maybe 1 million. So this is something you can have on your drive. What will not work, however, is 1 billion files on your drive that will actually break. This will not work. Why do we need 1 billion files? Well, imagine you are Apple, or you are, I don't know, any provider where like Dropbox, where people can actually store their data in their files. At the scale of the planet or even a country, you definitely will have 1 billion files. So that's what is telling us here is this just doesn't work, but just by attaching a drive to the network. And also adds to that the capacity of the drive is just going to be a few terabytes. All right, so these are the limitations. Which drives me to yet another question. Just need to make sure that you don't fall asleep. So how do you think, taking an example here with Elon Musk, how did we manage to make affordable electric cars with more range than was done before? So in the case of Tesla, there's anyway so many companies I'm dropping in the lecture that one more or one less doesn't really change much by now. All right, so he completely redesigned the car engine to consume less power. He completely redesigned the battery that would have more range, the BFB. He assembled plenty of cheap, widespread standard 18650 batteries, or you cannot tell us because you actually know. So we have a majority with assembling plenty of cheap, widespread standard batteries, and this is in fact the correct answer. And by the way, I hope you make the connection with the previous question on data centers, because there is actually a connection with the architecture of data centers. It's exactly the same idea. Right. So this is an example. These are the early ones, but now they keep changing the size. And of course, because there is innovation, but originally that's what it was. You just package plenty of cheap batteries like that in order to build a bigger one. I'm going to explain that to you shortly. Before we do that, here's what is going to happen in order to actually get cloud storage as a different way of doing things that on your local hard drive. First, we are going to throw away the hierarchy. We are just going flat, right? Just a flat list of files that we will call objects. Second, we make the data model trivial. We oversimplify things. It means that it's basically just going to be a key value model where you have an ID and the ID gives you a file or an object. We call them objects, right? So in fact, on the high level, it's just a map, right? It's a big map. There's going to be billions of IDs, maybe even trillions, but it is as trivial as it gets, right? You just associate IDs with objects. All right, and third, and that actually brings us on what we said on data centers earlier, we use plenty of cheap commodity hardware. This is how actually we increase the capacity and the scale outs. So what we get, and that's object storage, that's the first cloud storage system we will look into. We have a global key value model. Imagine billions or trillions of key values in there, right? And imagine that these objects can be very large, can be a picture, can be a video, can be an entire series episode, right? Can be very large. All right, and all of that is just sitting on plenty of cheap commodity hardware, right? So why are we doing it that way? Imagine that you have a machine. That's actually a problem that a lot of people have. You have a machine, you're running a program or querying data, but it's just too slow, it's not enough and so on. What can you do? Well, first you can just buy a bigger machine. That's called scaling up, right? So you can scale up and buy a machine with twice the capacity or twice the memory and just, you know, pay more, put more money in there and buy a bigger machine. The other possibility that you have instead of buying bigger machines is scaling out. So this is scaling up. You have scaling out. Scaling out means you don't buy bigger machines. You just buy more machines, the same, the cheap ones, the small ones. So you go ahead and just buy plenty of them. This is called scaling out. And in fact, if you look at it from a cost perspective, it is much cheaper to scale out than to scale up. It's very easy to see, because imagine how much can you scale up? If you scale up, let's say to, okay, 1 terabyte, that's fine, you can buy that. 5 terabytes, you can buy that. 10 terabytes, going to be more expensive, you can buy it. 20 terabytes, still works. 26 even works today, it's the maximum. What if you want a hard drive of 100 terabytes? Well, the only way you can do that is throw a few $1 million into an R&D facility that are going to actually build for you a hard drive, maybe in 10 years with 100 terabytes of data. So you see, the cost is exponential, right? If you want to actually scale up. But scaling out, it's much easier because it's linear at first sight. It's linear, right? Of course, now we know with today the problem with the supply chains and the price of raw commodities and so on, we know it doesn't scale, you know, eternally, right? You cannot just go like that on super large scales. But at least on the scale that interests us, like 10 computers, 100, 1,000 computers, the scale up is mostly linear, right? And there is an approach 3. Approach 3 is be smart. And what I mean with that is that if your program is slow or if you have trouble executing something, you might want to first check your code, because maybe there is an inefficiency in your code that you can fix to make it faster. You can look at your data. Maybe your data has duplication. Then you can deduplicate by removing the redundancy. Maybe you can compress. You can also use some compression methods in order to diminish the size of the data. You wouldn't imagine the number of use cases that you can actually fix to work on a single machine and save the costs of going into the cloud. That's the case of many early stage startups, actually, this idea that you can do a lot of things on a single machine. So this is why there is this quote that I really love, and I hope you will remember that you should only be allowed to use a second machine or a second computer once you know how to use the first one, right? Never underestimate the power of trying to squeeze everything you can from a single machine with better code writing, better ways to store data and so on. And only then can you go ahead and scale out, because we saw that scale up doesn't scale. All right, so in this lecture, we'll focus on approach 2, scaling out, which again doesn't mean that you shouldn't first try to write better programs and find more efficient ways to store, right? But we look into scaling out with plenty of machines. So we are going to now look into what there is in a data center. So in a data center, we saw there is plenty of cheap commodity hardware. Typically, there is between 1,000 and 100,000 machines in a data center. Typically, the maximum you find is typically 10,000, but we suspect, even though we don't know because we don't have all the numbers, that some companies might be beyond 10,000. What is important to understand here is that, so first, you have a lot of them because that's actually economies of scale, right? You find a single location and just put 1,000 computers on there. It's cheaper than having several locations, right? So that's why you already start with maybe 1,000 machines. Why not 100,000? The issue actually in a data center is the power, is the electricity, and that's the cool down in order to keep the CPUs from overheating. You have to imagine that that's what they told us when we visited the data center in a field trip. The energy consumption of a data center, like those you might find in the north of Zurich, is the consumption of an airport. It's the same consumption as the airport of Zurich, just so you imagine the quantity of electricity that is. You also have the cooling down, all the energy you need to use in order to cool down the systems. In fact, that's exactly the reason why at some places they use data centers in order to heat homes, right? So they build the data centers in a way that you can reuse the heat in order to heat the homes. But basically, this upper bound here comes from this. There is just a physical limit to how many computers you can have at the same place in such a way that you can supply enough electricity and that you can cool it down, right? So that's the main factor. Now, typical numbers, I'm just throwing numbers at you. On a server, you have between 100 and 200 cores. I'm rounding everything, right? So it's more like 128 currently, but it's just an order of magnitudes. You can have a lot of cores. Typically, when we talk about cores, we often talk in terms of virtual cores in a data center. You might have heard of hyper-threading, right? If you have a single physical core, you can actually run 2 threads on it at the same time. So from a virtual perspective, it's as if you had 2 cores instead of 1, right? So with hyper-threading, we can actually get more. But typically, you have, let's say, a 2-digit to 3-digit number of cores per server. Then, in terms of storage, you saw that today we go all the way to 26 terabytes, right? So I rounded up to 30, but this is going to continue to increase. In terms of memory, on your laptop, so this is where it might be different from your laptop. Because on a laptop, you probably have 16 gigabytes, 32 gigabytes, maybe 64. Who has 64 gigabytes of memory on their laptop? You do have, okay, some of you have. So you see, in a data center, the kind of memory you get can go beyond that. You can have a terabyte of memory, even all the way to 6 terabytes of memory. I actually found servers that had that much memory. But this is because it's in a data center and you might need a lot of memory. You will see it when you have memory, I don't know what error you will get, but memory overflow exception or that kind of things when you actually query your data. If you group data, it actually consumes a lot of memory. All right, then you have the network. The machines are connected over the network, and we'll see that this plays a role because of the latency of the network and the throughput of the network. So typically you have between 1, 10, 100 gigabits per second is the typical bandwidth you will get. All right. Now, here's the thing. I told you it's plenty of cheap commodity hardware, right, in the data center. Thousands, tens of thousands of machines. But if you go in a data center, what you will not find is plenty of tables with laptops on top of them. That's not how it looks like. In fact, in a data center, we pile up the servers on top of each other. We pile them up in what is called a rack. This is what it looks like. And you see here, the individual servers. You see, this is a server, this is a server, this is a server, this is a server. They are just piled up on top of each other. There's no screens. Who needs a screen, right? If you need to access them, you just do it over the network. So you don't need a screen. This is just a pile of computers right there. It is all standardized, meaning that the distance here, the size, is actually standardized. It's actually multiples of what is called RU for rack unit. So this is 42 rack units. And typically the height of what you put in there is 1, 2, 4 rack units and so on. So what you have there is the servers, we'll call them nodes. You can also have storage, meaning that on a single layer here, maybe you just put hard drives, plenty of hard drives. You might have routers, meaning that one layer will be just a network switch that's going to be used to connect, to centralize the connection of the machines, and so on. So as I told you, between 1 and 4 rack units is the standardized height, and this is how you can actually put them so easily in these standardized racks. Okay, so that's just an example. All right, so we actually are exactly, oh no, I still have 5 minutes. That's actually perfect. I can start with S3. So this is what we have in a data center, all right? We pile up nodes in racks in such a way that we get 10,000 of them connected over the network. And this is where we are going to store our data. All right, so that was the physical level of things, right? The physical implementation. Let's now switch the perspective and go back to the user, you, or whoever is using the actual cloud storage, seen from outside. Almost every provider, by now there's 3. There's basically Amazon, AWS, Azure, and Google Clouds. These are the main 3. There's also other players, but this would be nowadays the landscape. So let's look into Amazon S3, which is Amazon's cloud storage, object storage, more precisely. Who knows what S3 means? Yes? Almost simple storage service, but I might also be mistaken. It might be that it's solution. I double check. But in any case, SSS, you know, S3, simple storage service solution, right? So this is the way that you can upload and download objects. So the model looks like this. I'm very often going to do it that way, by the way, in the lecture. In the spirit of data independence, I will very often explain to you the logical model of a system without worrying about the physical implementation. And separately, we look at the physical implementation. So here, this is logical. There's no buckets, physical buckets in a data center. It's a logical explanation. So you have buckets, it's a logical concept that you can identify with a bucket ID. In some other providers, they call them containers, right? But in S3, they call them buckets. So if you have a bucket ID, you can uniquely identify a bucket. A bucket is controlled by a user, for example, you. That might be a bucket that you control. Maybe you have several buckets, but you can access one of these. And if you look at the bucket, it's full of objects. These are files. We just call them objects in the case of object storage, but these are files. And you identify an object with an object ID within the bucket. So that means that worldwide, because this is a service, it's a worldwide service, with a bucket ID plus an object ID, you can uniquely, unambiguously identify an object in S3 and, for example, download it. Worldwide. Anybody in the world, if you grant them the right, can use the bucket and object IDs and download the object. This is actually used. Let's take the example of Netflix or any streaming company. So what they are actually doing is that they are using typically all 3, because that way they also spread their data over multiple providers. So typically they use several providers, and they are going to store the videos on S3, on Azure Blob Storage, and on Google Cloud Storage. They won't actually store the full videos. What they do is that they actually slice the videos into smaller chunks. And then when they stream, they just download the chunk in the desired resolution and quality in an adaptive way, right? So the biggest customers of storage services like this are actually storage providers like Apple and streaming providers and so on, but any provider that needs for users to upload pictures, videos, files, and so on for online storage, all right? But as we will see, you can also use that for data sets, and that's a very popular way of storing your data sets. All right, a few more words. The maximum size of an object, there is a maximum here, is 5 terabytes. You cannot go over 5 terabytes in Amazon S3, all right? But we will see it's not a problem. It will not prevent us from storing petabytes of data. You can have by default up to 100 buckets per account. Within a bucket, you can put whatever you want, as many objects as you want, but the number of buckets cannot be beyond 100. The reason is simple. The namespace of the bucket is worldwide. If you create a bucket with a certain name, nobody else in the world can reuse that name. So if you didn't have that limitation, things could quickly get out of hand in terms of the naming of the buckets, right? So I think this is the main motivation. So up to 100 buckets. And if the break permits, where are we? Time was, oh, the break is arriving. So I'm going to leave you with these 9s for the break. I'm going to talk to you about them. It's lawyer language, actually, because this is legal stuff. The durability of the system is 99.999999999%, which means that every year you are losing 1 in 100 billion objects. There's no such thing as a perfect system, but every year you're losing 1 in 100 billion objects. That's something you have to accept. That's called the service level agreements, and I'll continue about that right after the break. So I'll see you in a quarter of an hour at 3, knowing that during the break we have guests from the analytics club who are going to present something to you if you're interested. Otherwise, you can go get a coffee as you wish, and then we'll continue in 15 minutes with the lecture. Thank you very much.